Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 10th, 2026, just 2 days ago. It introduces a framework called meta-experience learning that yields consistent improvements on reasoning benchmarks, specifically showing pass at 1 gains of about 4 to 5% across varying model sizes. The paper is titled, Internalizing Meta-Experience into Memory for Guided Reinforcement Learning in Large Language Models. And as we'll see later, the results are really impressive. Figure 1 compares the standard reinforcement learning with verifiable rewards approach against this new framework. On the left, standard RLVR relies purely on trajectory level optimization, meaning it simply encourages correct paths and suppresses incorrect ones based on the final outcome. On the right, meta-experience learning adds a secondary loop called knowledge level optimization. By analyzing the contrast between success and failure, it extracts meta-experience, specifically the bifurcation point, a critique and a heuristic, which teaches the model generalizable principles instead of just reinforcing specific paths. Figure 2 details the complete pipeline. On the left, the policy model generates a set of reasoning trajectories for a given question. The bottom path follows standard reinforcement learning with verifiable rewards, where the system calculates rewards and advantages for trajectory-level optimization. However, the top path introduces the new meta-experience component. By analyzing a contrastive pair of correct and incorrect solutions, the system identifies the specific bifurcation point where the error occurred. It then distills this into a critique and a heuristic, essentially converting the failure into a reusable lesson that guides knowledge level optimization. So, Table 1 quantifies the impact of this approach across 3 model sizes, ranging from 4 billion to 14 billion parameters. It compares meta-experience learning against the baselines on 5 math benchmarks, tracking pass at 1 for reliability and pass at 8 for consistency. The gains are robust across the board. For instance, looking at the average performance for the 14B model in the bottom right section, the pass at 1 score climbs from roughly 56% to over 61%. This shows that the internalized memory doesn't just help with exploration, but fundamentally improves the stability of the reasoning process. Alright, contrasting with those final metrics, Figure 3 illustrates the actual training dynamics across the 3 model sizes. In each panel, 4B on the left, 8B in the middle, and 14B on the right, the red line for meta-experience learning rises much faster than the blue baseline. This rapid ascent occurs because the internalized meta-experience acts as a dense reward signal, providing feedback at every step rather than waiting for a sparse final outcome. As a result, the model not only learns more efficiently in the early stages, but also reaches a consistently higher performance ceiling by the end of training. Well, Figure 4 provides a concrete case study on a geometry problem to show how this works in practice. On the left, the group relative policy optimization baseline jumps directly into calculations, but misapplies the formula by confusing a half angle with a full angle, leading to an error. In contrast, the top right panel displays the meta-experience component, which has diagnosed this pattern and formulated an angle verification rule as a safeguard. The bottom right trace shows the meta-experience learning model using this rule. It pauses to explicitly recall theorem properties and checks the angle definition before calculating, allowing it to reach the correct solution. Figure 5 now demonstrates that this strategy is broadly applicable, essentially serving as a plug-and-play enhancement for other training methods too. The left radar chart applies meta-experience to rejection sampling fine-tuning, while the right chart integrates it into the reinforce++ algorithm. In both comparisons, the inner blue line represents the base model, and the green line shows the standard training approach. Notice how the red polygon, which adds the meta-experience component, consistently encloses the others, pushing performance higher on every single benchmark axis. Wrapping up, the key takeaway here is that meta-experience learning effectively mimics human reflection. By converting transient errors into permanent generalizable rules within its memory, the model moves beyond rote trial and error toward genuine understanding. This shift from simple outcome verification to deep process refinement offers a promising path for more reliable AI reasoning. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.